Welcome to this video on mean and variance of a Poisson distribution. So the first thing you need to know is that if we look at the Poisson distribution, we have our parameter which is lambda. Now what is special about a Poisson distribution is that its mean and variance is the same. So if I think of my mean of my random variable x here, that's e of x or mu, and in this case it will be equal to lambda. And the same can be said about the variance of x. Remember, this is VAR of x, which looks like this, sigma squared, and that's also lambda. And this is quite an important concept. It helps you identify whether something is a Poisson distribution or can be modeled with a Poisson distribution if our mean and variance is the same, or in a lot of questions where you're using real world values, if these two values for the mean and variance are very close to each other, then it means that, or it's a good indicator that you could use a Poisson distribution to model that particular situation. So let's have a look at an example. So here we have a student investigating the number of cherries in a fruitcake. A random sample of 100 fruitcakes is taken and the results are summarized here. Now what we have to do first is calculate the mean and the variance of this data. So the mean is very straightforward, isn't it? If you remember, I'll just put the symbol down here. It's just going to be the sum of x divided by n, our number of pieces of data. So 143 divided by 100, so 1.43. Then the variance, well, this is going to be the sum of x squared over n minus the mean squared, isn't it? So we've got 347 divided by 100 minus my 1.43 squared. And that gives me 1.4251, which is 1.43 to 2 decimal places. So you can see here to 2 decimal places, our mean and variance are exactly the same, which is what indicates that it is a Poisson distribution, or that more accurately we can say that a Poisson distribution is a suitable model because the variance and the mean are equal to 2 decimal places, so they're almost exactly the same. And now I've basically explained part B, isn't it? Explain why the results suggest a Poisson distribution is a suitable model. So I have just explained it to 2 decimal places. The mean and the variance are equal. So quite simply here, I can put that the mean is approximately equal to the variance. It would probably be quite nice to maybe put a few words with it, just like I spoke, but that should be sufficient. But yeah, I would probably put a few words just like what I spoke, just mentioning that they are the same to 2 decimal places, maybe putting that little bit in there. Now part C is a straightforward part of the question, just like from previous bits. Now that you've established that it is a Poisson distribution and using a suitable value of lambda, well, the suitable value of lambda can be this 1.43, isn't it? That suitable value has got to be where they both round to exactly the same. So in this case it's to 2 decimal places. In other cases it might be 1 decimal place, it might be a whole value. It's where essentially where they round to give you exactly the same value. That means that we're looking at x being distributed with Poisson, and then for lambda I'm going to choose 1.4. Now I did talk about being the same value, and 1.43 is the same value for both. So I could, I suppose, use that as the value of lambda. The reason I'm actually using 1 decimal place is that my knowledge of statistics is very much limited to this A level, as in S1, S2. As you know, I taught this myself quite a few years ago when I first started teaching. So my knowledge of it is limited to what I've learned here, and I've never seen a value of lambda that's been more than one decimal place. Now, I don't know if it is fine to be more than one decimal place, or if it should be just be up to one decimal place. I'm not sure about that. I'm just going by, you know, from the questions I've seen, I haven't seen it be more than one decimal place. If you guys do find one, please point me in that direction, because I'd love to know. Because, you know, looking when I first glanced at this, we got the 1.43 is the same in both. So, you know, I would assume that I could use 1.43, but I'm going to use 1.4 for the reasons that I just said. Now, we're obviously going to find this when it's exactly 3. So we want to find the probability when x equals 3. So this is now e to the minus lambda times lambda to the power 3 over 3 factorial. And that gives me 0.1128 to 4 decimal places, or 0.113 to 3 significant figures. So up to you how accurate you do. You notice a lot of the statistics in here is often given to 4 decimal places, but you'll notice on the front of the exam paper it will tell you 3 significant figures unless it says otherwise. And that's, I think, probably why a lot of the tables and stuff will give you the 4 decimal places, so that, you know, all your answers, no matter how accurate they are, you know, whether you're using a calculator or the values in the tables, you should then get the same answer as everyone else to 3 significant figures. Now, I'm just going to do this one example today, as I don't think this is a very difficult or challenging topic. I'll give you a few questions to try, some past paper questions, and as always, I'll go through the answers at the end of the video. So I only found 2 past exam questions that have something with the mean and variance, you know, something where you have to find the mean and variance from given values. And it's this question, which is from January 2009, it's quite an old paper, and question 2, which is from June 2016. So here we have a question. We're going to do the whole question, but some of it's from, you know, early on in this Poisson distribution section. Now we've got a botanist studying a distribution of daisies in a field. The mean number of daisies per square is assumed to be 3. So we are looking at x is distributed Poisson, and lambda, our parameter there, is 3. Find the probability that in a randomly chosen square there are more than 2 daisies. So we're looking at the probability when x is greater than 2. Now remember, this means that it is greater than or equal to 3, which is 1 minus the probability that x is less than or equal to 2. And from here, since 3 is going to be in my tables, I can just go ahead and look up that value. And as you can see here, 2 is 0.4232, so 0.4232. And at this point then I go to my calculator and it's 1 minus that. And that will give me 0.5768, or 0.577 to 3 significant figures. Now part B says either 5 or 6, so x equals 5 or 6. So that is like the probability where x equals 5 plus the probability when x equals 6 if I was going to use a formula. Or equally, I could just do, because it's going to be using my tables, less than or equal to 6 minus less than or equal to 4. Because that's obviously 0 to 6, this is 0 to 4. Taking away 0 to 4 leaves me 6 and 5. So that's going to be the quickest way of doing this. So 6 here is 0.9665 and 4 is 0.8153, and then all I need to do is go to my calculator, and that gives me 0.1512 to 4 decimal places there, or as usual 151 to 3 significant figures. Now it's at this point we get to the part of the question that is very much linked with this video. We're given e of x and e of x squared. So part C says find or calculate the mean and variance. So if we're looking at the mean, that's going to be my sum of x over n, isn't it? So 295 divided by 80. As we can see here, we have 80 selected squares. And then it's just a matter of going to my calculator, and I get 3.6875. Now, I'm not going to round this one off just yet, okay, but 3.69, you know, is probably a suitable bit to round there, but I want to just find the variance first. So the variance is going to be the sum of x squared over n minus the mean squared. So we've got 1386 over 80 minus 3.6875 squared. So very straightforward then. In my calculator, 1386 over 80 minus my answer, my previous answer squared, and that will give me 3.72734 and so on. Now looking at these, they both round to to one decimal place as the same, don't they? So there we've got the 3.7. If I round the mean to one decimal place, I get 3.7. If I round the variance to one decimal place, I get 3.7. So that's a suitable place to kind of leave it. I could have left as 2 decimal places and then compared. Now that was obviously part C. Part D is explain. It's only worth 1 mark, but we can say that the mean is approximately equal to the variance. Okay, so you know, however then you want to go all about it, you know, you could say, if you did it to 2 decimal places, you could say that this 3.69 is approximately equal to 3.72, or you could say that 3.7 equals that 3.7, you know, when rounded to 1 decimal place. Something along those lines, you know, therefore Poisson model. Okay, totally up to you how you go about kind of saying it, but you're basically saying that these are almost equal to each other. And then finally part E is always about using that, if it did come up in a question. So part E is using the mean from part C, estimate the probability that exactly 4 daisies will be found in a randomly selected square. Now, if we're going to use the mean, we're not going to use this 3.7, are we? It's not, if it said use a suitable value of lambda, 3.7 would be the one. Now actually looking at this, this might be the first question I've randomly come across. I said earlier I never see it above 1 decimal place. This is maybe the first one that I have seen it, because it's specifically saying use the mean. That makes me want to use that whole value, doesn't it? where effectively I am looking at a Poisson distribution of that mean, so 3.6875. So we're looking at exactly 4, probability when y equals 4. So that is e to the minus 3.6875 times 3.6875 to the power 4 over 4 factorial. And this will give me 0.19286 and so on, which is 0.193 to 3 significant figures there. So interestingly, and I've just double checked the mark scheme of this, and indeed they have used that full value as well. So I was right to use the full value there. And I kind of answered my question from early on in the video. So I've found a question where it uses more than one decimal place, so we could have happily used 2 decimal places in that example question. So as I said, this one's from June 2016, and we get straight in with it, mean and variance. So finding the mean is going to be the sum of x. So I'm going to do that on the bottom just underneath here. So the sum of x is going to be adding up all my values. Now in this case we have a frequency, so it's actually going to be the sum of fx, isn't it? Okay, so that's what I'm finding first of all. So I've got 0 times 24 plus 1 times 37 plus 2 times 21, and so on all the way up to the 5 times 2. And I can ignore that greater than 6, there are 0 of them. So finding this out, I get a total of 141. So my mean is going to be 141 over, and it's going to be the sum of the frequency. Okay, and it doesn't give it to me in the question, as sometimes it does, so I just need to total up my frequencies, and that will total 100. So my mean here is 1.41. Next I need to find the variance. Now as you remember, the variance is now going to be the sum of fx squared, isn't it? So that means it's 0 squared times 24 plus 1 squared times 37 plus, and so on all the way up to 5 squared times 2. That will give me a total of 343. So we've got a variance of 343 over 100 minus 1.41 squared. And that gives me my variance of 1.4419. So we've now found our mean and variance. Part B says, explain why the results in Part A suggest a Poisson distribution may be a suitable model for this. So we can clearly see that these two values are very close to each other. So I can say for Part B, that our mean is approximately equal to our variance, as in 1.41 is approximately equal to 1.4419. In fact, if I take them to one decimal place, then they are the same, aren't they? They both round to 1.4. So this is like kind of correct to one decimal place. So that's another way of putting it, but it's only worth one mark mentioning, my mean is approximately equal to my variance, or the mean is close to the variance, and putting those values down is really helpful. Now, part C tells me that we now have a mean of 1.5. So we're looking at a Poisson distribution where our value lambda, or that parameter, is 1.5. So C now, part 1, is exactly 2 cherries. So we want when x equals 2. 1.5 is in my tables, so I do have an option. So I'm going to use the formula, but I'll show you with the tables as well. So e to the minus lambda times lambda to the power of x, which is 2 over 2 factorial. And this gives me 0.2510 to 4 decimal places. Now, if I use the tables, another way of doing it would be as follows. So I'd go x is less than or equal to 2 minus x is less than or equal to 1. Okay, and that would then give me, you can see here there's the 2 and the 1, so it'd be 0.8088 minus 0.5578. And this would also, normally I would write x equals 2 here. So just go into my calculators, 0.8088 minus 0.5578, and in my calculator I get 0.251, which you can see is the same to that 3 significant figures, or even 4 decimal places, as the next one is 0. So it is useful. You can use the tables to speed up your answer sometimes. If it's just the 1, I think it's pretty straightforward just to use the formula, but you can use the table. Now we've got part 2, at least 1 cherry, so greater than or equal to 1, isn't it? At least 1. So 1 minus the probability that x equals 0. And again now, if I use the formula, I can find that value of 0 quite quickly, as it's 1 minus e to the minus lambda, which is 1.5. Then if we think about it, lambda to the power 0 is 1 over 0 factorial, which is 1. So here I've just got 1 minus e to the minus 1.5, which will give me 0.77686 and so on, which I'll round off in a second. But just before I do, I'm going to show you, using the tables. So alternatively, 1 minus this p where x equals 0, here's 0 in the tables, isn't it? So we've got 1 minus 0.2231, 0.2231, and that gives me from the table 0.7769. So you can see now, here is all from tables. Yeah, and what you can see here is that this value is this value. Look, round that 6 will make this 8 round to a 9, and we've got the same answer. So I would actually go 0.77. I'd either leave it as 69, or I could go to 73 significant figures. But like you can see here, using the tables can be quite quick and easy, and there's no reason not to use them if you do prefer. But if you do prefer using the tables, just at the end round it to 3 significant figures, I think will be a better way to kind of finish your overall question, but using the kind of full values where you can. Now part D gives us a little bit of a difference. So now we're told that the fruitcakes are sold in packs of 5. So before our value of lambda was 1.5, wasn't it? Because it was a mean of 1.5 cherries per fruitcake. Now we're sold in packs of 5, we need to multiply this by 5. So that's going to give me 7.5. So now I'm going to change it to y, and the Poisson is going to be 7.5 for that value of lambda. And that's really going to, that's where all there is to this one. It's nothing too difficult. Yeah, it's just recognizing that that's what it's asking you to do, isn't it? If you don't spot that, then it is going to be a bit of a problem. Now we've got here, show that the probability there are more than 10. So y is greater than 10. So this is y is greater than or equal to 11. Remember, always make it so that your inequality has that equals in it. So that means it's 1 minus the probability that, sorry, I almost drew an X there, is less than or equal, y is less than or equal to 10. So again, I'm going to go to my tables. And here you can see that 10 is the 0.8622. So 1 minus 0.8622 is going to give me 0.1378. It wants it to 4 decimal places, so I would leave it like that, and you can see up here that is the value that we were expecting, so we're all good. Finally, part E. Now, the final parts of these questions will often be something different, like an approximation, which is chapter 3, which is what we will be going on to next. Or sometimes from the Poisson, it might ask you about a binomial. These are the two kind of most common bits for the end of these distribution questions. So you can see here, this one is going to be a binomial. So I just want to change this up now. New distribution is binomial. Okay, so we've got, and what you'll always notice is that we're talking about something that we've already done. So you'll notice that this more than 10, this is what was in the last one. That's what we were finding, that probability that there are more than 10. But now we have a number of packets, and we have a total number of packets that have been taken. So n is 12, and the probability of more than 10 is our 0.1378, which we found in part D, but we were also given in part D. So we could have done this part E regardless whether we could do part D or not. Now what I'm looking for is the probability that A equals 3, so exactly 3. So remember now our NCR, our 12 and 3. Then we've got 0.1378 to the power 3, and then we've got 1 minus that 0.1378, and that will be to the power 9. Remembering that these should always total our value of n. After this, then it's just a matter of putting it into my calculator, and I get 0.15158 and so on. So let's do 152 to 3 significant figures. A lot of the time these kind of questions, especially the older ones, will give you to 4 decimal places, but what you'll always usually notice in the question that you'll see an AWRT answer which rounds to, and that will usually be then 3 significant figures, and that's always going to be in there. And they've got to, really, because the front of the book or the front of your exam paper says round to 3 significant figures unless otherwise directed or otherwise told. Hopefully you found this video useful. The next one, or the next set of videos, is going to be on our approximations. So this is now going to be normal approximations from S2, which we can approximate both binomial and Poisson with, and also we can approximate binomial with a Poisson distribution in some cases. Okay, so in some certain scenarios Poisson can be used to approximate binomial as well. So we'll have a look at those in the next set of videos.